Designing cooling systems, the role of heat exchangers explained. Imagine trying to keep a hot cup of coffee from cooling down too quickly or a computer chip from overheating. That's where heat exchangers come into play. They are the unsung heroes in many cooling systems, helping transfer heat efficiently without mixing fluids. Understanding how they work can make a big difference in designing reliable and effective cooling solutions. Heat exchangers are devices engineered to transfer heat between two or more fluids. These fluids can be liquids or gases, and they stay separate during the process. The main goal is to move heat from a hot fluid to a cooler one, keeping equipment and systems within safe temperature limits. This process relies on three key mechanisms: conduction, convection, and radiation. In most cooling systems, conduction and convection are the primary methods used. Let's look at some common types of heat exchangers. The shell and tube design is very popular. It features a series of tubes inside a larger shell. One fluid flows through the tubes while the other surrounds them inside the shell. This setup is sturdy, easy to clean, and suitable for high-pressure applications. Plate heat exchangers are another option. They use thin metal plates stacked together, creating multiple channels for fluids. These are compact, with a large surface area that allows for quick heat transfer, making them ideal where space is limited. Fin tube heat exchangers add fins to increase surface area further. They are especially useful when air is involved, like in air conditioning units or industrial cooling. Designing an effective heat exchanger depends on several factors. First, heat transfer efficiency is vital. The goal is to transfer as much heat as possible in the shortest time. Next, the properties of the fluids matter. Their temperature, pressure, viscosity, and heat capacity influence how well heat is transferred and how much resistance the fluids face. The flow arrangement also plays a role. Counterflow setups, where fluids move in opposite directions, typically transfer heat more effectively than parallel flow arrangements. Material choice is important too. Metals like copper and stainless steel are preferred because they conduct heat well and resist corrosion. Minimizing pressure drops is another key aspect. If the fluid faces too much resistance, it takes more energy to pump or blow it through the system. Therefore, balancing surface area and flow rates is essential. Engineers calculate the necessary surface area based on parameters like the overall heat transfer coefficient and the temperature difference between fluids. Proper sizing ensures the system can handle the required cooling load without wasting energy. In real-world applications, heat exchangers are everywhere. They keep engines cool in vehicles, help in heating, ventilation, and air conditioning systems in buildings, and recover waste heat in factories. For example, in refrigeration systems, heat exchangers act as evaporators and condensers. They absorb heat from the environment or releases it, all without mixing fluids, which keeps the system efficient and safe. By understanding these principles, mechanical engineers can design cooling systems that are both effective and reliable. Properly chosen and sized heat exchangers help maintain optimal temperatures, prevent overheating, and save energy. Whether in industrial plants, vehicles, or buildings, these devices are fundamental to managing heat transfer smoothly and efficiently.